time to let everyone knows you and where you are, because I know some last time students asking where it is. So we have Joanne, we have Yimeng, and we have Minghao. Yeah, there. Okay, yeah. So this time, except for a notebook, we actually have 3 data, which I will introduce later. So basically, you just need to go to the Canvas, and then you click on Files, Tutorials, and now we are on the 4th class, so the TO4. And then we first download all these files with this icon, which means that they are not PDF or PPT. So just download them. Yeah, so just unzip them. Yeah, I hope you're on board, right? You have repeated this so much time. So and then you go to Google Colab. Just type Google. Just enter Colab in Google, and you'll find the site. And then go to the files, and then upload notebook, and then just drag this .ipynb file to the web page, and then after a few seconds, you will load to your site. Yeah, so the notebook should be like this. It starts with a mean image, and I will explain to you later. And then while you like reading the comics, you also need to upload all of these data files. So in total, we have 3 files today, and then just drag here. Or you can click this upload icon and then select the files you want. So after that, it will appear here. So I think you have done this so many times. So any questions so far? Or haven't encountered any issues? No? Okay. Yeah, so then let's get started. Yeah, so you still remember in the very last 10 minutes of our course or lecture this morning, we introduced a concept called the FPKM. So don't be so confused by the name. It's just trying to account for 2 main bias. The first is about a gene name, because you can imagine if a gene is longer, it will be more likely to be sequenced or be captured by your sequencer. So in order to cancel out all of these bias or the effect by the gene length, and also the difference in the sequencing depth, which means for this sample we got 200 million reads, and for the other sample we only got 100. So their total read number are different. So they will definitely cause problem. So the purpose of this FPKM is actually trying to cancel out the effect caused by these 2 factors. So basically, they just divide the amount of the map fragment of your gene, on a gene of your gene of interest, divide them by the total number of mapped fragments, which accounts for the sequencing depth, and also the exon length of the transcript in kilobase, which will account for the gene length. So, any questions? Okay. So this is just the first step of the pre-processing. Actually, you still have following step that will still account for other kind of noise inside your data, and we will actually introduce them in the Thursday lecture. But here I'll just introduce it briefly. So the next step is called the variance stabilizing transform, or also called VST. This is the reason that we're going to use it, we're going to apply this VST on our data is that because, for example, this is just an example that I simulate on my laptop, and then I would like to share with you. So you can see if I want to plot a scatter plot between X and Y, and then you can see that when X value is very small in this kind of data, the Y variance is pretty small. So you can see that all of the points are actually fall within a small range of Y. However, when X go large, you can see that the Y value become more and more unstable. So you can see, so this is why the variance is unstable, because it kind of depends on the data or the mean value that your variable is. So actually, after applying this BST transform, which is basically put a function on y, so it will become fy, or the BST transform y, you can see that the relationship between the x and y become pretty stable like this. So actually, in our data, after the FPKM transform, our next step is trying to account for these effects. And here in our tutorial, we'll just simply use the so-called log2 transformation. So just simply taking the log of the value of y. And although it's not a perfect BST, it's kind of like pseudo BST, and we will see later that how this variance is being stabilized after this transformation. So this is the second step. And then the third step is called the quantile normalization. So this logic is still simple. So you can see in this diagram or in this plot on the left, you can see, so these 1, 2, 3 are actually samples. And then each dot represent one gene, and then dots with the same color means the same gene in different samples, okay? So in this example, we only have 4 genes, and then you can see that their gene expression distribution are different between samples. And some people will consider them as a batch effect between the samples. So they hope that the gene expression distribution will be similar between the samples. So that's why they would like to perform so-called quantile normalization. And after that, you can see that all of the dots or all of distribution are the same among samples, except for the orders of the genes. So their gene can still be differentially expressed. However, all the gene expression falls within the same distribution. So this is called a quantile normalization. And yeah, we also introduced the algorithm on Thursday. And then lastly, it's called a z-score transform. So this is kind of a simple step. It's just, or I would call it scaling, because it's just doing some linear operation on your data like after the quantile normalization. So so basically we know that for any distribution, there will be 2 parameters. One will be the mu, which is the mean of the distribution, and the other is the sigma, which is the standard deviation of this distribution. So actually, we just would like to do some linear transformation such that after this z-score transform, the mean value will become 0, and then the standard deviation will become 1. So yeah, that's the simple logic. And then this is all for the pre-processing. And then after that, in our tutorial today, we also would like to explore some like pretty simple EDA. It's called differentially expressed genes, or DE, we are differentially expressed DE analysis, and also visualize them using the volcano plot. So basically, it does a very simple job. It just for each gene. So first of all, you will define the group you would like to compare. For example, the control group and the experimental group. And then for each gene, we will perform a t-test, for example, comparing the expression distribution between the groups. So, and then after the t-test, we will get a p-value, right? And then also the log4 chain. So, which means the mean expression of the gene, it is a ratio of the mean expression of one gene. So, and then we take the log value. So after that, if this log fold chain value is positive, it means that this gene is differentially expressed in sample in a control sample or experiment. Depends on how you define them in your calculation. And if the log fold chain on the other side, which means that this gene is differentially expressed in the other group. So and then if we plot the scatter plot where the x value is actually the log fold chain, and then the y value is a log of the p value, so a negative log of the p value. So larger of the p, this kind of negative log p value, the more significant it will be. So this kind of volcano plot will just help us visualize what are the most important genes that separate these two groups. For example, here these all the like the important genes, like so let's call it, they are labeled here. So this is basically the introduction of the code for today. And then this time we will actually explore another cancer called prostate cancer. And this is just some illustration of where this cancer will be and what it will be look like. And then we actually got a 175 samples with so many genes, and also we got a lot of clinical features, for example, the age, the gender, and etc., or how malignant this tumor has been diagnosed. And we also like ask a question, which is to look for the differentially expressed genes between the patient diagnosed with high risk and intermediate risk. So and then this is just a summary of the step we are going to. I think it's kind of a standard step of processing this kind of bulk RNA data. So first of all, we'll get the FASTQ file. So we all know what FASTQ is, right? And then we make a BAM file, and then got the count matrix, and then calculate the FPKM, perform the VST transform, and then point out more scaling. And then for today, we will only start with here, because the previous two steps is super resource consuming. So yeah, all the data are the raw read count. So yeah, let's start with our coding today. And same as last time, I'll also set up a ask anything board. So you can just type anything you feel confused. Let's see how I can. And if you scan this QR code, you can just type something to let me know it works. Okay, hi, okay, great. And interesting. This is out of the scope of this course. Okay. Okay, this is also out of the scope of this course. Too difficult. Okay, so I'll just leave a. Let's see how. Okay. Anyways. Okay. So let me enlarge the page a little bit. So for the guy sitting on the back, can you see? Is it clear, or I need to enlarge? Good. Okay. So so I just put a mean here. Just it's a screenshot from Simpson. So the Homer. So we know that like in scientific journals, people like showing the best view of their data. And actually, in reality, almost every data on our hands are pretty dirty or pretty noisy. So actually, so if we are just reading journal, we see how good their data is. Actually, in somewhere you didn't see, they actually did a lot of data preprocessing work, and they just I cannot say they just hide it. They just don't emphasize how much work they have done on like cleaning their data. So that's why we have this tutorial today. So yeah, if your collab session didn't get expired, I think you can just yeah. Oh, I forgot a file. It should be the sample data. Sorry, let me upload it. Yeah, let's do this again and see your comments. Thank you. Okay, and yeah, so it should work. Then, if you got any question or encounter any issues, just type in here. So so basically, we have three data, and what do they mean? So first, the DA object actually just a column matrix. So you can see each column represent one sample, and each row represent a gene, which is by this gene, which is named by the gene ID, and you can convert them to a readable gene symbol. But here I just didn't. But I will do this later. So just would like you keep you guys in mind. This is just a column matrix, and then the other is called the anode. This data frame just store all the information of each gene. So each column is the gene ID, which are same here, and then we just get what this gene is called, and then their function. You can just read it, or you just ignore them. So and then lastly, we got the meta, which store the clinical information of each sample. So you can see here each row becomes a sample, and then each column is essentially a clinical feature. Yeah, just store. I think you can just scroll. There should be more. Yeah, there will be 45 clinical features here. Yeah, so these are basically the three data we are going to play with. And first of all, it's called the FPKM transformation. And you have learned the formula, which is the amount of gene fragment mapped to the gene of your interest, and then divided by the total fragment in samples and the gene length in base pair, and times this 10 to the power of 9, because there are a lot of the unit transformation, and this is a more readable way. So we first calculate the RPM. So these two are just equivalent. So first of all, we calculate the RPM, which is the denominator here, and then divided by total fragments in sample times 10 to the power of 6, because it is million. Okay, because per million map reads. So that's why we need to multiply with this. And then to calculate the FPKM, we just divide it by gene length in kilobase. So I think a question for you, but I think we don't have time for you to answer. Just keep you in mind. I think you all know this. So what kind of effect you will cancel out after this FPKM transformation? So next, I would like your help again, because you have some work to do, and basically just trying to implement the function based on the formula here. I think it's just exactly the same as this formula. You just need to input these two lines. I think will be difficult. If you encounter a problem, just type here. And I'll also do it for you right now. So for this function, we have some input. So the input parameters are count series, which is just a recount for a gene, for all genes in a sample. So it will be a vectors, and each values contain the raw count of a gene. And then this is the information storing where the length of each gene. So basically, we just need to follow the formula here. So I have already calculated the library size, which is just the total fragment sample. So we just need to divide the count series by the library size and then multiply it with 1 million. Is it 1 million? No. Okay. It should be 1 million. Okay. So this is RPM, and then for the FPKM, we just need to divide these RPM by the length, which is given by this parameter, the length KB series. And then we just run the code again because we need to let your computer know this function, what this function looks like. So to check whether your calculation is correct, you just need to run the next cell of code, and then it will just calculate the FPKM using the function you have written. And then we just and then they will store the FPKM transform values in this FPKM table. And then if you print them, and then I also make a model answer here, so you can just compare the values. If they look same, it means that you are correct. So I will give you some time and questions you can just type in or you can speak up. I would prefer speaking up. Or if you're done or if you still need more time, then I see some of you still typing. Take your time. Yeah, so I think I can move on. Okay, so that's for the FPKM. So you can see that after this transform, the raw counts become before that they are all integers because they are just raw counts, and then after this transformation, they are not integers. And then we will move on to the BST. So which I have mentioned in our tutorial, we will just apply the logarithm by on the FPKM data. So you can see how it behaves in your figures that I will show you later. So this is just a formula which is taking the log of this expression value, which is the FPKM plus 1. So you guys know why we need to plus 1? Like, what if I just delete them, right? Yeah, we got 0, right? Yeah, correct. So yeah, actually we just add a pseudo count on each gene such that because if we just put 0 inside, the log will become error, right? We don't like errors. And so that's why we add a pseudo count. Actually, it might cause some problem, but you can see how like this kind of pseudo counts, the effect are not that large compared with the real scenario. So if you just run this code, it will just give you a plot showing the mean expression of a gene. So each dot represents one gene among all the samples, 175 samples, and then the y value or the y-axis are the variance of the gene expression among all the samples. So you can see a pretty unstable variance, as you can see that if the mean expression is low, the variance will also be low. And if the mean expression is high, the variance will be extremely large. because the y-axis actually are plotted on log scale. So you can see how unstable their variance is. So next, we need to do the VST, right? So another work you need to do, just follow this formula. Just calculate this log FPKM. So remember, after FPKM, all the values are stored here, FPKM table. So because in lecture we haven't covered this, so I will just do it right now because it might make you confused. So just basically apply the log to, and remember, don't forget the serial count. Oh, I see a question. Where do the count series and the length come from? You can see that here we actually define a function. So if we use the function, the first argument will be the count series and the second argument will be the length. And then here is where we use it. So the first argument is the count and the second argument is the length. So I think that explains. Okay, then let's go back to here. So I hope you have input this line of code, just a pretty simple log to transform. And then if we run it, and then we can see how the variance and the mean related. So now we can see that the variance does, although it doesn't look like super or perfectly stable, we can kind of see that the variance are not that depend on the mean value. So that kind of shows us how this kind of log2 transformation will stabilize the variance in our RNA-seq data, or more or less stabilize. So any questions so far? Any? Or I'm talking too fast? No? So I'll assume you understand. Or you guys, anyone confused about the plots? No? Okay. Okay, then good. Let's move on. Yeah, I'll just leave these questions for you because of the time. So next, we are going to do a called quantile normalization. So I have just mentioned the quantile norm is just trying to make the gene expression distribution across samples to be the same. So we will cover this in the lecture on Thursday. So I will not introduce too much here. So so basically, this figure it is a screenshot from Wikipedia, and if you just follow the steps. So first of all, we rank the gene expression. Also, A, B, C, D are just different gene names, and then the numbers here are just the sample. So we will first rank the gene expression along the sample. So for sample 1, the highest expression is 2, so it will become 1, then 2, 3, 4. So for each sample, we will do the same thing, and then this is and then we will leave this data here, and then we will do another operation on the original matrix. So basically, we just sort the numbers along each column. So you can see that each value here are just sorted in a ascending order. So after that, we calculate the mean value of each row. So for the first row, the mean is 2, and the second it is 3, etc. So then we get a value mapped to a rank value, right? Because this is the first rank and get this value. So then we apply this kind of rank map to this rank value that we have computed. and then we will give us the final quantile norm result. So I know it's kind of complicated, too complicated to understand here. So I don't assume that you all know what I'm talking about. And actually, but I think you can still run this code by just copying the code from me. And so first of all, we can just have a look at, so here I will just pick two samples and see and compare the distribution, the gene expression distribution between these two samples using QQ-plot. So in case someone don't know how to read this kind of plot, so if two distribution are perfectly distributed, they are perfectly same. So they're perfect. They have a same distribution. So all the points will fall along this diagonal axis. And here you can see that when the values are small, I think the distribution between these two samples are kind of good or kind of the same. However, for those like the market or the high express genes, on the tail here you can see a deviation from the diagonal axis, which means that the distribution kind of deviates between these two samples on this range. So that's how you read this, and then we need to do a quantile normalization on our data. So basically, another work you need to do, but as you might not know what this algorithm looks like, so you can just copy the code from me. So the first step is to sort each column. So just type in np.sort on, because we are also making functions. So we sort the df, and then we need to specify. We need to sort according to the rows or the columns. So for the column, you can just read the hint here. It should be 0. And then next, you need to compute the mean of the sorted data frame along each row. So the index should be 1. You can read the hint by yourself, or you can just copy down and it should work. And then we just press run. Yeah, I'll just give you some time to do the copying, and I'll read your comments. Okay, normal speed. Is there a simple example to explain the variance varies with the mean? It will be a bad thing. Yeah, that's a very good question. I will explain to you if we still have time, or you can just come to me afterward, or you can just wait for the lectures. I think it will be covered. And so I think you all finished writing the code, and then we can just run the next bunch of code. It will just plot a QQ-plot comparing the gene expression distribution between these two samples after the quantile norm. So you can see how it becomes a perfect linear distribution. So you can still remember before the quantile norm. I think the distribution are similar but not that perfect, right? Or not exactly the same. So after the quantile normalization, you can see it become like identically distributed. So this is how the quantile norm works. And then lastly, we're going to perform this z-score transformation. So as I had mentioned before, it just did some linear operation on your data. So your data means the expression, like the value after this quantile normalization. So basically, it just subtract your value with the mean value of your of the gene, and then divide them by the variance or the standard deviation of the variance, the standard deviation. So just by math, it will guarantee that all the resulting value will have mean 0 and the variance as 1. So z here is the score after the is the value after the z-score transformation. And here is a question that I would like you to think about. So because we know z-score transformation, z-score is kind of linked with the normal distribution. So I'm asking, I want to ask, does this kind of z-score transformation will yield a standard normal distribution data? So I hope you guys know what I want to ask. And you can just type in here or yeah. Yeah, I saw a note here, but I'm not sure whether this note answered this question. Yeah, so the correct answer is no, because it just cancel out, it just do some linear transformation to assume to guarantee the mean value to be 0 and then the standard deviation to be 1, and that's all. So we actually cannot make it a perfect normal after this transformation. So here are the codes. We can first plot a histogram of a gene. So the gene name is here, or the gene ID is here. So you can see how the expression of this gene distribute among the samples. So you can see their mean value are definitely not 0, right? Because all values are positive. And then yeah, so they are not the z-score transform one. And then we can just implement the z-score transformation. Another work you need to do, and I'll also do this for you. So remember, after the quantile normalization, we store all of the values in this quantile norm table. So we just need to calculate the mean expression. And of genes, so it should be row-wise, because the count matrix, each row represents a gene. So it should be a row. And then we calculate the standard deviation. And I've given you the hint here. Yeah, it should also be row-wise. So after that, you can just run the code. And then it just give you some values after the z-score transform. Plus, we'll also give you a few seconds to run the code. And is everyone still on board, right? You don't get lost. If so, you can find me afterwards. I'll try to help. And also you can find TAs. They're working on QA now. Yeah, so after that, you can plot the distribution again. So you can see that their mean value become 0 here, like from the eye, and you can also calculate there should be 0. And then the other thing, if you compare the shape between the distribution after the z-score and before the z-score, actually they are the same. So we don't change the shape of the distribution. We only do the so-called linear transformation on the values to kind of scale the distribution, not changing the shape. Yeah, so after the z-score transformation, I think we are basically uh, finished the pre-processing part. So for the remaining times, I will just introduce a tiny little bit about the kind of, or you can also call it the EDA. It's trying to identify the DE genes, the differentially expressed genes. So basically, just calculate the p-value for each gene, so to see which gene will differentially express in a group. So because if we do DE genes, we need to define the groups here. So here in this demo question, to compare the gene expression between the high and intermediate risk group, we first need to define which group are in high risk, so which group are in intermediate risk. So it's actually stored in metadata variable here. I just mentioned you these data frames store the clinical data for each sample. So if you run this cell, you just store the two groups information here. And then we just calculate the DE genes. And here, fortunately, you don't need to do any coding here, just need to push the run. And it might take a few seconds because they need to calculate the they'll perform the test for each gene. And we have like almost 40,000 genes to calculate. So it might take you a few seconds, but it won't be that long. Won't be very long. Should be finished within a minute. Okay, it's longer than 1 minute. Okay. Anyways. Not always. Yeah, not always. Okay. So mine start within 1.5 minutes. So I think you will be more or less similar than me. So here you can see after this D gene, you can see so each row is a gene. So you got the log 2-fold change. So it is negative, which means that it is differentially expressed in the group in one group, and positive, which means it is in another group. And we also get a p-value. We also get the p-adjusted, and it's just for the multiple testing. So you can, if you are interested, you can just Google it. So basically, if we are performing tests, so we are performing a lot of tests, we should not use the original p-value anymore because if we still keep the p-value to 0.05 and if we perform 100 tests, it will be like 5 tests will be so there will be false positive, and if you only see 5 like around 5 positive result, I think most of them might be just fake. So that's why we will adjust the p-value. So basically, after this DE gene, we will trust the p-value here, not the original one. So you can see that after the adjustment, the p-value become larger actually because they will take account for the multiple testing. And after that, just run the last bunch of code. It will just give you a volcano plot, and you just made it by yourself. So you just by yourself. Why not? So just show you a differentially expressed genes between the two groups, and I think in our experiment, the upregulated means the genes that are upregulated in group 1. I think it's in. Okay, just anyway, I actually, you can check it by yourself. So all the genes here are those D genes that you identify, and for each group. So yeah, and that will be so much for the coding. And as for the question some of you asked here, so why the stable variance is important, and I think I can draw it to make it more intuitive. So if we get a x-axis and y, if the data kind of like this, so let me see. So or let me make another. So in group 1, there are two groups, group 1 and group 2. And we would like to compare a value. For example, in group 1, the dots will fall within this range. And then if you make a box plot, it should be like this. And then for G2, the variance is large. And then if we make a box plot, it should be something like this. And then if we would like to see a difference between these 2 points and the difference between, let me use another color. So basically, for group 2, we just want to compare these 2 dots. And then for group 1, we would like to compare these 2 dots. So which difference you think are larger or more important? If we just compare their absolute value, they are similar, right? However, because in group 1, this is actually the lowest value. This is highest value, so this should be important. I'm not sure whether that will explain. This should be important within this group. However, if we compare G2, because the variance is so large, this difference is not important because it's just a small difference within the group. Not so the term that I would say is as important as G1, this group between the comparison between this should be like this. And that's why before we making comparison, we would like to make the variance of each gene to be stable, such that we can compare their difference just by directly subtracting their values. Yeah, it's kind of complicated. I hope they will work. That will explain. And yeah, and I think that's so much for today. And enjoy dinner. And you can find me for any questions. Legend on the volcano is incorrect. Okay.
Right. So I give a very good coding reuse the code and try it. So on Thursday we will talk about theory panic, like why we are. branch from data